approximate method through which we can get a solution. The solution may not be exact, that will be your approximate solution. Apart from weighted residual method, we also have variational approach through which we can get an approximate solution. So here we will discuss weighted residual method. So here you just see we are talking about weighted residual. Okay, so there will be some weight function, and there will be residue. So here we learn how basically weight function is operating on the residue and how we are getting the solution. Now before going to that method, any method of the weighted residual method, let us understand what is basically residue. Before going to the residue, we should know what is our solution. So we know, if for example, if we know that L phi, okay, if you know the value of L phi, okay, value of L phi is equal to minus F, then we can say that basically phi is our exact solution. Okay, that is our actual solution of our differential equations, and there will not be any error. Okay, now instead of phi, okay, if you use psi, if you use any other function psi, then that value will not be minus F. That value will not be minus F. Okay, so that will be any other value than the minus F. So what we can say, then L in L psi plus F will not be 0 now. There will be some error, will not be 0 now. There will be some error, and that error basically we are saying residue. So here this is our residue. Okay. Now what are the weight functions? Now what weighted residual method is saying? Weighted residual method is saying that you take a weight function and multiply with that residue and try to make the error 0 in the whole domain. Okay. So here in the you are making the 0, you are making the residue 0 in the whole domain through a weight functions. Okay. So basically we are making the error 0 in an average sense. Okay, we are making the error 0 in an average sense over the domain. Okay, so now if we put the equation here and if we do the integrations, you can make it 0. Okay, now here in the weighted residual method, we have to follow some steps. So follow some steps in the sense we will understand how basically we can work on that weighted residual method. So in that weighted residual method, what we have to do? We have to assume a trial function. Here we are assuming psi. Some cases you will observe that we are assuming phi as a trial functions, but here just see we are assuming a trial function or approximate solution. One more thing you have to remember, that approximate solution need to satisfy the boundary condition of that actual problem. Okay, for example, if you have a cantilever beam, then actual solution also satisfying actual problem, actual solution you are satisfying that here displacement will be 0 and rotation will be 0 if you consider cantilever beam. Okay, here displacement will be 0 and your rotation also will be 0 in the end, fixed end. So your approximate solution or the trial solution also need to satisfy the same boundary conditions. Okay, so once we assume a solution, trial solution or approximate solution, then what we will do, we will put the solution in the differential equation. You will put the solution into that our original equation. Okay, now if you put the equations, then we will get the error. So basically we will get that error, that is basically calling as a residue. Okay. Now this residue we need to make 0 in average sense over the domain. So what we'll do, we'll take the help of a weight function and multiply the weight with that residue and we'll integrate over the whole domain and we'll make the residue 0 over the domain in an average sense. This is basically weighted residual method. Okay. Now in the weighted residual method we have various methods. Okay. We have various methods, and here we have various methods. So in various methods, we have very popular method. That 4 popular method we have, that is your Galerkin method, square method, point collocation method, and subdomain method, that also called subdomain collocation method. So these all 4 methods basically differ on the basis of how basically we are assuming the weight function. How we assume the weight function, depending on that, we have 4 methods. Okay, so here in this lecture, we will try to understand the Galerkin's weighted residual method. Before going to that Glarkin method, let us make it clear that here we'll try to assume two trial function. First trial function we will assume trigonometric function, and second trial function we will assume as a polynomial function. Okay. Now here one more thing you have to keep in mind, that you can assume any trial functions, not necessarily trigonometric or polynomial. You can assume mix of it also, provided your trial function satisfy the boundary condition of exact problem. Okay, or you can say you need to satisfy that your trial function or approximate function need to satisfy the boundary condition of actual problem. Okay, or your actual solution, what are the boundary condition it is satisfying, your trial function also need to satisfy the same boundary condition. So here what we will do, we will try to assume two trial functions. One is trigonometric trial functions, and we'll see how we can apply your Clarkin's method and how to get the solution. And second, we'll basically apply polynomial function in the form of C0, C1x, C2, x square, like that. And trigonometric functions, here we'll assume that ck sine pi x, k pi x by L. Okay, you can use cos k pi x by L, or you can use tan, you can use any other function, provided that function satisfy the boundary conditions of actual problem, or trial functions or approximate functions satisfying the boundary conditions of your actual solution. Now here limitation is that not necessary that all the approximate solution will converge to your exact result. Okay, in some cases you observe your trigonometric functions giving good result, some cases you will observe your polynomial functions will give result. Okay, one more thing, that if we use higher order polynomial, then also it may happen that you are not getting good result. Okay, not necessary, it is not necessary that if you use higher polynomial, in that case you will get that good result. Okay, it's not like that. Okay, so what we do, we have to give some trial using some defined trial functions or approximate functions, and you have to see whether you are getting the good solution or not. Okay, here what we'll do, we'll take one example problem. That example is here, your one simply supported beam, and at the two end we are applying moment m or m0. We are applying the moment m0, and we know this is the solution for this problem, and we'll try to see what is the approximate solution. Okay. So this is our exact solution. We'll try to find our approximate solution. In some cases we may not have the exact solution, so you have to go for some trial and use your trigonometric functions, you can use your polynomial functions, you can increase your higher polynomial, and you can see whether you are getting close result or not among the three methods. Okay, three method in the sense, trial, your trigonometric approach, polynomial, and your higher order polynomial, lower order polynomial and higher order polynomial. You can use different polynomial and you can see whether you are getting good result or not. Okay, so if now here for this problem we have that exact solution, and we have the boundary conditions. The boundary condition is here, simply supported beam. So your y will be 0 at x is equal to 0. Again, y will be 0 at x is equal to L. So this is length L. Now we know that for this problem, we have that moment, that value of the moment is ei dt by dx2. That value is 0. Okay. Now what we'll do, in that Glarkin weighted residual method, what we'll do, we'll basically use one approximate function or trial function. Okay, so our trial function is here a sine pi x by L. So we are writing in terms of C1 N1. Okay, because you will observe that most of the book use to write in this form. Okay, now question is that here we are using one trial functions. I already informed that you can use combination of various parameters. Okay, so trial function can be combination of two parameter, a sine k pi x by L. Again you can write a 2 cos pi k pi x by L, like that. Okay, so in that case whatever you do, you have to write you can write the trial functions or approximate function in this way, c1 c2 n2, like that. Okay, so now if you have two parameters, summation of the two parameter, in that case you have to basically integrate for the two functions, again you have to make it 0. You have to basically basically assume the weight functions and you have to multiply with that error. Okay, and again weight function you have to multiply the error and you have to make it 0 separately. Okay, so once you make it separately, you can take the summation of it. The overall domain, the error in the overall domain will be 0. Okay, so here what we are doing, we are taking one trial functions, that your a sin pi x by L. Okay, a sin pi x by L. So now we are writing in terms of C1 N1. Now what we are doing, we are taking double derivative of these functions. Okay, so once we get the double derivative and once we put this value into this equation, okay, that value will not be now that initial our equation was ey d2y dx2, that was equal to m0. Now what I did, I just put instead of y, I just put the value of u. So now this value will not be m0, there will be some other value. Okay, so we can write ei du dx2 minus m0, that is equal to some error. So we're writing in terms of error like this. So error, if we write, okay, if you write the error, okay, if we write it, so basically we will get your ei, that value sin pi x by L minus m0, that is our error. Okay, now here we get the error. Okay, now once we come to our Galerkin method, so we will see how we can assume the weight function. So here we get the error. Now in the Galerkin method, what happened, we used to assume the weight function same as your trial function or approximation function. In the Galerkin method, weight function, that weight we assume same as your approximation function or the trial function. Okay, so our trial function here was u. Okay, so y is our original solutions, but we assume u as the trial functions, and in the Galerkin method, in Galerkin weighted ratio method, we assume weight function as the same as your trial function. So basically w will be u, that is equal to c1 n1. Okay, now what we do, we have to make the error 0 in an average sense. So basically we used to operate the weight function on the residue and we have to make it 0 over the domain like this. So now what we will do, we will write wr dx, that is equal to 0. Okay, that basically we will write. Okay, now here, so there will be c1 n1, residue, that will be 0. Since c1 is a constant term, we'll take it out. So our basically our equation will look like this. So our equation will look like this. Our equation will be like this. Okay, n1 r x dx is equal to 0. Okay, so this is we have to do this. We have to do now. Our basically, what is the value of n1? N1 will be here sin pi x by L. Okay, n1 will be sin pi x by L. Okay. Now what we have to do? We have to basically put the value there, and we have to do the integration, and we have to find that unknown coefficient here. So this part is known to us. Okay, this part is known to us. What I did, I put the value here, w into r. I will make it 0. W we assume c1 n1. Okay. Okay. Once we put the value here, w that here the value c1, so it was 0. Okay. We already observed. So c1 will making this side, so it will be this one n1. So value of n1 is basically sin pi x by L. In bracket, this value, that error is coming. Basically, this is the error. We are putting it here, and this is our weight function. Okay, so weight function in the sense weight function w, that was our same as u, and that is our c1 n1. Okay, so once we put that value, so c1 is constant, we are making this side. Okay, so this is the equations we are getting, and what you have to do, you have to do these integrations over the domain 0 to L, or the domain 0 to L. So once you do that integration over the domain, what you will get, you will observe that this one a was one unknown coefficient here. M is moment, that is applied moment. Okay, that will be given. Only A magnitude, that we assume now A sine pi x by L, that we assume that A was unknown. So basically once we make it 0, if once we make that W into R is equal to 0, we will get the value of A. Okay, now our trial solution or our approximate solution is coming like this. Okay, and we know our exact solution. We know our exact solution look like this, and trial solution look like this. Now here you can see, here you will see these two equations look different. Now if you want to compare whether the solution you are getting, whether your approximate solution and exact solution is close or not, whatever you do, you have to plot it. So if you want to plot, then you have to assume some data. So you have to assume what is the value of M0, what is the value of E, what is the value of I, okay, what is the value of L. So this parameter I assume and I plot it. Okay, so what I get basically, this line is your exact solution or actual solution, and red line is your approximate solution. Here you can see these two values are very close. Okay, though one is sine function and this is your x L minus x, look like different thing, but once you plot with that value, numerical value, you will get that the basically our approximate solution and your actual solution very close. So this is acceptable. Okay, now what we will do, we will go for another, we'll go for another type of solution where we'll assume our trial function, we'll assume our trial function, okay, phi or psi, whatever you can assume, trial function as a polynomial. Okay, here we'll assume a trial function as a polynomial. Now again, I am saying that our trial functions need to satisfy, the boundary condition it has. Okay, so for this sine function, here you can see, it was, basically satisfying the conditions automatically. Okay, so if you put x is equal to 0, our trial function value was 0. If we put the value x is equal to L, our the u value was coming 0. So basically you can say this was basically satisfying that boundary condition that actual problem has. Okay, or you can say whatever the actual solution was satisfying, the boundary condition, the actual solution was satisfying, our approximate function also satisfying the same thing. So here, since we're using polynomial, so what have to do, we have to satisfy the boundary conditions. Okay, so that we can get that, or we get that approximate solution which is basically replicating our physical problem. Okay, which replicate our physical problem. So what we'll do, we'll put u is equal to 0 at x is equal to 0. If you put that, you will observe from this equation, okay, you will put that your u is equal to 0 at a, even that you will get a is equal to 0. So here one more thing, let me clarify. Here what we are doing, we are basically taking one trial solution as a, b x and c x square. Okay, like that. So you can use higher order term. Okay, but here we restrict ourselves with that t term. Okay, a b x c x square. Now what we'll do, we'll put u is equal to 0 and at x is equal to 0, you will observe a is equal to 0. Now one more section, one more boundary condition into satisfy that u is equal to 0 at x is equal to L. If you do that, you will get that b is equal to minus L. Okay, now if you put that value into this equation, you will observe that our solution is basically coming. Our solution is coming like this. So you can write u is equal to c x L minus x. Okay, you can write u is equal to c L minus. So in that way, you can write that your u is equal to c1 n1. Okay, so here again you have to keep in mind that c1 and c are the same value. Okay, so since this is the popular notation every book used to follow, so I am writing in this format. Okay, you can put any other coefficient here, the c. Okay, you can put any other constant there. So we are writing our trial function in this way, that u is equal to c1 n1. Okay, that is equal to the same thing here. Okay, where n1 is equal to your x in bracket x minus L. Okay, now we agree that our u will be like this because it's also satisfying the boundary condition of our actual problem. Okay, now what we'll do, we'll again take the double derivative of u, okay, and we'll put the value here. Okay, so again, if we put the value here u, then this will be our error. Okay, so our error will come as like this. Our error will come as like this, ei2c minus m0. That will be our error. Okay, now once we know the error, our Galerkin method, it is saying w into r dx over the domain will be 0. So basically we are making the 0 over the domain as ever. Now here again our weight function will be same as your approximation function. Okay, so our weight function w will be the same as u as your c x minus l. Okay, now if we put here w into r, that is just c, okay, x minus l, and this is term our error term. This is our error term here, making 0. So c is a constant. You can take it out, make it 0. So this part will be 0. So this part only will be 0. Okay, so this part will be 0. Now here you can see we have only one unknown. This c term is unknown here. Okay, once you are there, that was basically outside the bracket, we just make it 0. Now once you solve it, you will get the c value. Okay, once you solve this problem, you will observe that c is equal to m0 by 2 ei. Okay, so m0 by 2 ei. So here c is equal to m0 by 2 ei. So our approximate solution is your m0 2 ei by x in bracket l minus x. Okay, here minus is there, so here also minus is there. So here you can see our actual solution and approximate solution are the same. So if you plot it, you will get both the solution basically will come one by one. Okay, it will be overlap with our actual solution. Okay, so here you can see that our polynomial approximation is giving good result in comparison to our trigonometric approximation. Okay, but again I'm saying that this may not be the case always. It may happen that you may not get a good solution using polynomial. Even if you increase that order of the polynomial, in that higher polynomial, if you consider, in that case also you may get your exact solution. So this is one limitation we have. Okay, so what we do in that case, you can use combination of trigonometric function and the polynomial, or you can combine two defined trigonometric functions to get our approximate solution. Okay, so I hope you get some idea. Thank you.